Okay, so one of the ideas we run into with acids and bases is that not all of them are strong, meaning when you put them in water, they don't always dissolve. And with some substances, they hardly dissolve at all. So, for example, let me just use hydrofluoric acid because it's quick to write HF. If you put HF into water, the reaction that theoretically will occur is HFs will meet water molecules. The HF will give away hydrogen to produce hydronium, and we'll be left with some fluoride ions. Now, the trouble is, the equilibrium constant for this is actually very small. And what that means is the equilibrium is way to the left. If you put HF in a container of water, so you have tons of H2Os, and by tons I mean 4 because there's not a lot of room in this diagram, and then you put in a bunch of HFs, most of those HFs are not going to do anything. Most of them will float around, holding on to their hydrogen, not acting like acid, not doing much of anything at all. Occasionally one will. And so you'll see a small amount of H3O and you'll see a small amount of F minus because some of the HFs do dissociate. It's just that most of them don't. And so you end up with a lot of unreacted acid and a little bit that has dissociated or ionized. And they use the amount that has ionized as a rating of how strong the acid is, and they call it the percent dissociation or the percent ionization. And it's a way of gauging how active an acid is when you throw it in water. So the way you find percent ionization in my example would be to say, I threw in 4 HFs. Here's 1, here's 2, here's 3, and there's the 4th one. So in my case, the total is 4. How many ionized? Just 1. If you go looking for H3Os, which are evidence that an acid broke up, you only find 1. And so you'd get 1 out of 4, which is 0.25, or 25%. So based on my simplified numbers here, you'd say this acid has 25% ionization. That's what we're going to be doing for this next little stretch. We're going to be checking acids and bases to see how strongly they reacted. So it will be fun. You will love it. Let's get in there. Okay, so here, they start with an acid at 0.1 moles per liter. So that's the total amount that we put in. Now, how much of it dissolved? Well, we find 1 times 10 to the minus 4 moles per liter of H3O. So this acid is supposed to be turning into H3O. 1 times 10 to the minus 4 moles per liter of it actually did. If you make a fraction out of that and divide it out, if you do 1 times 10 to the minus 4 divided by 0.1, I get 0.001 from that, or if you multiply it by 100, you get 0.1%. So this acid is rather feeble. Less than 1% of it actually released hydrogen. The rest of it just floated around not doing anything. For this one, we put in 0.5. That's our total amount of acid. How much of it released hydrogen? 2.5 times 10 to the minus 2. If we divide that out, we get 5 times 10 to the minus 2, or 0.05, or if you multiply that by 100 to turn it into a fraction, you get 5% ionization for this one. Stronger than part A, still not real impressive. Now we can do this with bases also. You could look at a base and say, how much base did I put in, and how much OH am I seeing now? And if a base created an OH, then it's active, and if it didn't create an OH, that means it's just floating around being lazy. So for this, we'd say the total amount of base we put in is 0.01. That's our full concentration. The OH concentration, we don't have it. I want OH to go here. Can we get it? Well, yeah. If the pH is 8.47, then our POH should be 14 minus that, which is 5.53. And then our OH is 10 to the minus 5.53. Two 0.95 times 10 to the minus 6. So that is our amount of OH. I can put that in our numerator here. 2.95 times 10 to the minus 6. Okay, so 2.95 times 10 to the minus 6 divided by 0.01. Our ionization fraction is 0.000295. And if we multiply that by 100 to make it into a decimal, we get 0.030. Oh wait, this has two significant digits, so I guess 30 is the best I can do. 0.030%. Not a strong performing acid. And for this last one, we have a base. Its original concentration was 0.5. That's how much base we put in. How much OH did we get? Well, POH is 4.4. And that means the hydroxide concentration is 10 to the minus 4.4. Three significant digits, this will be 3.98 times 10 to the minus 5. So that's how much hydroxide we've made. So 3.98 times 10 to the minus 5 divided by 0.5. So our ionization fraction is 0.0000796, or multiply it by 100 to get a percentage, and you get a tiny, tiny bit of 1%. Just as an aside, if we had something like HCl, let's say we had 0.5 moles per liter HCl, 0.5 moles per liter H3O. If we did this calculation, we'd get 0.5 over 0.5 equals 1 equals 100%. That's what it looks like for a strong acid. The top 6 acids, every single one of them turns into an H3O, and you'll get 100% rating. So if you ever do this and you get 100%, it means you're talking about one of the top 6 acids. If you get some much lesser number or anything under 100%, you're talking about one of the weak acids, one of the many weak acids. Okay, just a few more of these. Actually, these are a slightly different question, but it's still working with partial dissociation. Or no, these are strong. My bad, so this might be a little simple. If you put a strong acid, like hydrochloric acid, in water, 0.1 moles per liter, every single bit of it turns into H3O. So this concentration will be exactly the same as the original acid was. How much of the original acid will you find? None at all. Every single bit of it broke and turned into hydrogen ions and A minus, whatever that is. So you won't find any intact acid. How much dissociated acid will you find? Exactly as much as you did hydrogen. In other words, if this original acid was, let's say, HCl, this is asking how much H plus will you find? Every one of these will produce an H plus. This says how much HCl will you find in the solution after a little while? None. It's all dissociated. And this is saying how much chloride will you find? Plenty, because all of these HCl's broke up. How much hydroxide will you find? Okay, now we have to do a bit of a number crunch. If the H3O is this, then the pH is negative log of this number. The pH is 1. That means the POH is 13, because the P numbers have to add up to 14. And that means the hydroxide is 1.00 times 10 to the minus 13. Because hydroxide is always 10 to the minus POH. All right, so these first 3 we just get from knowing it's a strong acid. This last one took a little bit of work. If we have a strong base, something like hydroxide, if it's a strong base, then the hydroxide is exactly the same amount. 0.3 moles per liter. A strong base is something that is 100% effective at turning into hydroxides. So however much base you put in, that's how much hydroxide you will get. How much base will you find after the reaction's gone? None, because all of these bases will have tackled water molecules and stolen their hydroxide or their hydrogen, sorry, and you'll have this instead. All of them will do this. So every single B will have turned into an HB. There won't be any plain old B minuses left. What will be the POH? Well, if we know the OH concentration is 0.3, you just negative log that, and you get that the POH is 0.523. And the P numbers have to add up to 14, so if one of them is 0.523, the other one must be 13.477. Okay, a species present in the highest concentration in a 0.1 mole per liter solution of formic acid. Okay, so formic acid is a weak acid. It's not one of the top 6. So if you put it in water, in theory it wants to do this. It wants to give away hydrogen and become HCOO and produce H3O. Unfortunately, the K is extremely low, so if you put formic acid in water, what you're going to get is a lot of left side, a lot of formic acid floating around in water not doing anything, and you're going to get hardly any formate and hydronium ion. So the species present at highest concentration in a 0.1 mole per liter solution, well, this concentration will be 0.1 moles per liter pretty much. It might be like 0.099 because a tiny bit of this is dissolved, but it'll be very close to still 0.1 because of the low dissociation level. Technically, the concentration of water in just a container of water is about 55. I think it's 55.85 moles per liter. That's the concentration of pure water. So that's going to be very high, and very little of it will have changed because this reaction's not happening very much. The HCOO will be very low. Actually, both of these numbers should be pretty much the same because when you make an HCOO, you make an H3O at the same time. So these are like low and equal. Now, when they asked this question, I honestly don't know if they meant for us to include water. So the technically correct, but maybe not what they want answer for this is that water is the most concentrated species in that solution. But if they mean of the acid products, of the 3 interesting ones, then the clear winner is HCOOH because almost all of these will float around in the water unchanged. There will be very little of these guys. Fair enough. And last one, 0.2 moles per liter of HW, which is an acid, I guess, is dissolved in water to make a solution. Okay, so I don't know precisely what HW is, but I guess because it has a hydrogen in it, it wants to act like an acid. It's capable of doing this. HW will give away a hydrogen. The water will pick up a hydrogen. And that will happen. How much does it happen? I'm not sure, but I think they're about to give us some numbers, so let's find out. They say the OH is 1 times 10 to the minus 9. From that we can get POH. POH is negative log 1 times 10 to the minus 9, which means the POH is 9. The pH would be 14 take away 9 would be 5. And from that we can get the H3O. The H3O would be 10 to the minus 5. Okay. What are we doing with this? Okay, so the original concentration of this was 0.2. They tell us that. It's up here. The amount of H3O we're getting is 10 to the minus 5, which is like 0.00001. This should be the same amount because these are produced simultaneously. Every time you make an H3O, you make a W at the same time, so their concentrations should pretty much match. Uh, so we got the H3O. How much W is there? It should be 10 to the minus 5 also, because those numbers are the same. How much HW is there? Very often we will fudge it and say 0.2. We'll say there's hardly been any change, so this concentration is unaffected. Technically, though, the really good answer is we started with 0.200 and then we lost 0.00001. And so it seems like the answer should come back 0.19999. Here's the problem. According to significant digit rules, when you subtract a number that has 3 decimal places and a number that has 5 decimal places, you can only trust the answer up to 3 decimal places. In other words, this number is 0.200, don't really know, don't really know. Those were not measured precisely. That means when we subtract this, I mean, you might subtract and get 0.19999, but now we have to cut this down to 3 decimal places, and when we do, guess what? We get our 0.200 back anyway. This is like saying someone's got $20,000 or something, and then we steal a cent from them. In the end, you can't even see the difference. It's like stealing a penny from the Coca-Cola Corporation. You can't even see it in their bottom line because the starting number is so much bigger than the amount you just lost. After a little bit of round off, you can't even find the difference that you made anymore. And so that's another reason why when we have a weak acid and we get its concentration, we just say the concentration you had before is pretty much the same concentration you will have afterwards because the amount that dissolves doesn't even make a dent in the total amount usually. There's some exceptions to that with things that have a very high K or a very low concentration, but in general, you can expect that whatever this for a weak acid or weak base, whatever the original concentration is, it will be unchanged afterwards. The little bit that dissolves is not enough to affect this.